Today we're explaining embeddings, the mathematical black magic that convinced us vectors can capture human meaning. Not the clean words become numbers version from tutorials, but the real implementation where king man plus woman equals queen somehow works. Your similarity search returns garbage, and you realize we've compressed all of human knowledge into floating point approximations that we don't understand. 3 AI engineers, 1 mathematician who's questioning the nature of meaning itself, and 45 minutes of pure vector space horror. I'm Sam, and someone just asked me to explain why cat and dog are 0.73 similar.
I've been working with embeddings for 6 years. 6 years. The papers make it sound elegant, distributed representations, semantic similarity, vector arithmetic, reality. I spent 3 months debugging why doctor was closer to man than woman in my embedding space, then realized I'd accidentally encoded centuries of gender bias into 300 floating point numbers.
My job is making these fucking things scale. You know what happens when you try to store 100 billion embeddings? Your vector database becomes a memory-eating monster that costs $200K per month to run. We had a similarity search that took 45 seconds because someone embedded the entire internet into 1536-dimensional space.
I study how embeddings relate to human meaning. Spoiler alert, they don't. They're statistical approximations of word co-occurrence patterns that accidentally stumbled into something that looks like semantic understanding. It's the most elaborate statistical parlor trick in computer science.
Dr. Akafor, you're our guide through this semantic hellscape. Elena and Jake, prepare to explain why cosine similarity became consciousness. No mercy, no hand-waving about learned representations.
Let's start simple. What is an embedding?
It's a way to represent discrete objects like words as continuous vectors in high-dimensional space, so we can do math on meaning.
That's marketing speak. What are you actually doing to words?
Converting them into lists of numbers. Cat becomes for maybe 300 or 1536 dimensions. Then we pretend that vector arithmetic on these numbers somehow captures semantic relationships. It's numerology with extra steps.
How do you train these embeddings? What's the learning objective?
Word2Vec uses skipgram or CBOW. You predict context words from target words or vice versa. Words that appear in similar contexts get similar vectors. It's like guilt by association, but for semantics.
Show me the math. What's the actual objective function?
For skipgram, you maximize log probability, sigma log PW context W target. The probability is softmax of dot products, XVC/sigma XV. It's just a big neural network trying to predict word neighborhoods.
What's this famous king man plus woman equals queen example actually showing?
That vector arithmetic sometimes captures analogical relationships. The difference between king and man approximates the concept of royalty, so adding that to woman gets you near queen, but it's cherry-picked. Most analogies don't work.
Why does this work at all? What's the theoretical justification?
Nobody really knows. The distributional hypothesis says words with similar meanings appear in similar contexts, but why that creates linear relationships in vector space is still mysterious. We're doing computational linguistics with no linguistic theory.
How do you measure similarity between embeddings?
Cosine similarity is the standard. Cos theta equals a b/a times b. It measures the angle between vectors, ignoring magnitude. 2 vectors pointing in the same direction are similar regardless of length.
Why cosine similarity instead of Euclidean distance?
Because high-dimensional spaces are weird. In 300 dimensions, almost all points are equidistant from each other. Cosine similarity looks at direction, not distance. It's the difference between how far apart and how aligned.
What's the curse of dimensionality doing to your embeddings?
Everything becomes equally similar in high dimensions. Your nearest neighbor search returns random garbage because all vectors are roughly the same distance apart. We're fighting against the geometry of high-dimensional space.
How do modern transformer embeddings differ from Word2Vec?
Contextual embeddings. BERT gives different vectors for bank in Riverbank versus Moneybank. Word2Vec gives the same vector regardless of context. It's the difference between static meaning and dynamic meaning.
What's the computational cost of these contextual embeddings?
Insane, BRT base has 110 M parameters just for embeddings. OpenAI's ADA002 embeddings cost $0.01 per 1K tokens. Embedding a large corpus costs more than my car. We're paying transformer prices for vector representations.
Now the practical nightmare, vector databases. How do you search billions of embeddings?
Approximate nearest neighbor search. Phi Zanoi SKA-NN. You trade accuracy for speed. Exact search is ON, but ANN algorithms can get you close in logarithmic time. Close being the operative word, you're not getting exact matches.
What are the different indexing strategies?
LSH, tree-based methods, graph-based indexes, each has trade-offs. LSH is fast but approximate. HNSW graphs are more accurate but memory-hungry. There's no free lunch in high-dimensional search.
What about the bias problem in embeddings?
They amplify every bias in the training data. Programmer is closer to he than she. Nurse is closer to woman. We've encoded centuries of prejudice into mathematical representations and called it objective.
Can you Debias embeddings mathematically?
Sort of, you can project out gender directions or use adversarial training. But bias is multidimensional and intersectional. Remove one bias, three more emerge. It's like playing whack-a-mole with social prejudice.
What happens when you try to embed rare words or concepts?
Out of vocabulary nightmare. Words the model never saw get random vectors or get broken into subwords. Technical terms, proper nouns, domain-specific language, they all become noise in embedding space.
How do you handle multiple languages in embedding space?
Cross-lingual embeddings try to align vector spaces across languages, but it's messy. Languages have different concepts, different metaphors. You can't just rotate vectors and expect semantic alignment. Meaning doesn't translate linearly.
What's the biggest limitation of current embedding approaches?
They're frozen snapshots of meaning. Train on 2020 data, your embeddings don't know about 2025 concepts. Language evolves, but embeddings are static. Plus, they collapse context into a single vector, massive information loss.
Final question, do embeddings actually understand meaning?
No, they're statistical patterns that correlate with meaning. They capture co-occurrence, not comprehension. It's like saying a map understands geography, it represents relationships, but has no understanding of what those relationships mean.
And we're building entire AI systems on this foundation. Retrieval augmented generation, semantic search, recommendation systems, all based on the assumption that vector similarity equals conceptual similarity. It's a house of cards.
Jesus Christ, so we've compressed human meaning into floating point approximations. Nobody knows why vector arithmetic works, and we're using cosine similarity to measure the distance between concepts. This is fine.
Welcome to 2025. We're building the future of information retrieval on statistical word games and calling it semantic understanding.
This episode was brought to you by Engineer Panic, where we strip away the embedding hype and show you the vector space reality. Because understanding why your similarity search is fundamentally broken is probably important. We're back, let's talk about the practical nightmare of actually implementing embeddings at scale. Elena, what's the most frustrating part of embedding development?
Evaluation, how do you measure if your embeddings are good? Word similarity benchmarks are tiny and biased. Downstream task performance is confounded by a million other factors. You're flying blind most of the time.
Version management is hell. Update your embeddings and suddenly all your similarity searches return different results. Your entire application behavior changes because you moved from word to vec to BERT. There's no backward compatibility.
And the interpretability problem, users see similarity, 0.73, and assume they understand what that means. But it's cosine similarity in 1536-dimensional space based on statistical co-occurrence. The number is meaningless to humans.
What about the computational costs? How expensive are these vector operations?
Brutal. Embedding 1 billion documents with OpenAI costs $100K, then you need vector databases that can handle similarity search across billions of high-dimensional vectors. Your infrastructure costs explode exponentially.
And the memory requirements are insane. Store 100 million 1536-dimensional embeddings and you need 600 gigabytes just for the vectors. Add indexing overhead and you're looking at terabytes of RAM for decent performance.
The opportunity cost is what kills me. We're spending billions optimizing vector operations instead of understanding what meaning actually is. We've mistaken the map for the territory.
What keeps you up at night about embedding systems?
That we're building critical systems on fundamentally flawed representations. Search engines, recommendation systems, AI assistants, all relying on vectors that encode historical bias and statistical noise as if it were truth.
The illusion of precision. Users see similarity scores to 3 decimal places and think it means something. But it's approximate nearest neighbor search on biased vectors in incomprehensible dimensions. The precision is fake.
That we've given up on understanding meaning in favor of measuring it. We treat semantic similarity like distance in physical space, but meaning doesn't work that way. Context is everything and embeddings throw it away.
Any advice for engineers working with embeddings?
Understand your domain deeply. Generic embeddings trained on Wikipedia might not work for legal documents or medical texts. Always evaluate on your specific use case, not benchmark datasets.
Plan for scale from day one. Vector operations that work on thousands of embeddings break spectacularly at millions. Also, budget for way more memory and compute than you think you need.
Stay skeptical, question every similarity score, every nearest neighbor result. Remember that embeddings are tools, not truth. They approximate human meaning, but they are not human meaning.
This has been Engineer Panic. We've learned that embeddings are statistical approximations of meaning that somehow work despite being fundamentally broken, and we're building the future of AI on them. Sleep tight.
Thanks for the semantic crisis, Dr. Akafer. Now I'm going back to debugging why love and hate have a similarity score of 0.84 in my embedding space.
And I need to explain to my manager why our simple semantic search requires a server farm that costs more than a small country's GDP.
Keep building, keep questioning, keep remembering that vectors are not meaning. The future of AI depends on engineers who understand the difference between correlation and comprehension.
This has been Engineer Panic. where embeddings meet existential dread. Until next time, remember, cosine similarity is not semantic similarity, no matter how much we pretend it is.